So this last section is on optimal control problems, so OCPs. And these are a way of configuring complex multi-phase optimization problems. So taking those phase structures we had and formulating and transcribing problems that are too complex to solve with a single phase or have different behaviors that you need within the same problem. So a multi-phase optimal control problem in asset is a way to formulate some of the more complex trajectory problems that have, as the title says, multiple phases required. So one example that James has in his dissertation, I know yesterday we pointed to the dissertation as well as a good example, is a launch vehicle with a recoverable first stage, where you launch the entire stack of the vehicle for one phase, and then you separate and you send one part of the vehicle into some constrained target orbit, while at the same time you send the other part of the vehicle back down to a target point to land and be recovered. So that's just one example of a multi-phase optimal control problem where you can have multi-objective and different constraints for different phases of flight. So for optimal control problems, we're using Asset's optimal control library. So remember, we've imported from Asset, we've imported asset.vector functions as VF. We also, to get those ODE arguments, imported asset.optimal control as OC. So it's that optimal control, that OC library in Asset, where we can formulate these optimal control problems. And the way to picture what these optimal control problems are is, once you have the different phases instantiated that you need for this combined problem, you can write an OCP that links all of those phases together, and you have all of your phase-specific transcriptions, you have all of your phase-specific objectives and constraints. Now with an OCP, you can patch all of those phases together into one problem, and it also lets you patch together and apply constraints on how these phases might be constrained relative to each other, or add objective functions on inputs or functions that require components from different phases. So you've got all of the phases independently defined now. Then you use the OCP to link them together. So here we could have a multi-objective problem, and objective functions in different phases are summed together. So you're minimizing the sum of your individual objective functions if you're doing a multi-objective. And of course, that is relative to a weight that you can place on the objectives to scale the weighting of what you're trying to optimize. Of course, you're also still solving all of the constraints, minimizing the sum of objectives of your phases, solving all of the constraints applied to each phase, and now you can append on constraints and or objectives to the phase linking components. So when you solve an optimal control problem, it's solving all of your phases in parallel and adding to the standard optimal control equation any link constraints that we've added where you're linking phases. So creating an optimal control problem is quite simple. You just instantiate an optimal control problem object from the optimal control library. And then now you have an empty optimal control container, essentially, and you can append and add phases to that optimal control problem. So again, I know I've reiterated it, and this will make sense, hopefully make more sense with exposure to examples. But the optimal control problem comes after you defined and constrained your individual phases of the mission. Then when you're ready to patch them together and add any constraints or objectives between those phases that are instantiated and defined. Now you create your optimal control problem, add the phases in. Now the optimal control problem has these members that are your phases. So phase index 0 is the first phase that you passed in. Index phase OCP.phase index 1 is the second phase that you passed in. So you now have them all pulled together. It's important to remember the phases that you've added into this optimal control problem are the exact same object. So when you solve an optimal control problem, if you want to know what's the optimized trajectory in the first phase that I added to the OCP, you can just take that first phase 0 dot return traj, and it's giving you the trajectory that that phase did. It is the actual phase itself that's being operated on within your optimal control problem. It's not instantiating a different phase for the optimal control problem.
Are you defining the optimal control problems as an optimization above the phase optimization problems? So, like, you have integrator is just a propagator, right? And then you have phase, which is an optimization of a section. Are you defining optimal control problems as an optimization of multiple phases, so that you're kind of like optimizing the optimization problems? Do you see what I'm saying?
Is it one big problem, or is it optimizer on top of?
No, it's one big problem. It just takes all of the phases, all of the constraints that would be applied for one phase, and poses them all at the same time. Yeah, it's not doing any like DDP or differential dynamic programming where it like solves each of the phases individually, like recursively. It's solving it all together.
Yeah, so it's just the way you link them together to have one big multi-phase problem.
Right. Yeah, and just so we can reuse everything from phase, it's just kind of you take the existing phases and put them in an optimal control problem. It's just the higher level of organization. We don't want to have like a different interface for doing multi-phase versus single phase, so you just reuse the single phases and put them together.
So, but each of these phases would be using co-location segments in between, V0 and VF0 and VF1.
Each of these phases, since you're configuring them individually, can have different transcriptions.
Yeah, different transcriptions. They can have different dynamics.
Okay.
They don't even have to be the same ODE, so long as there's some consistent way to link them up. So you could have like a ballistic model that, or like something that's like a launch vehicle that lets off like a low thrust spacecraft or something like that. There's no constraints on that. I mean, there's no restriction to have the same ODE or anything like that.
Yeah, and we'll get to examples that even use different ODEs for different phases, and I think we do the same transcription, but you as a user are allowed to change.
Yeah, you can do whatever. Like, a lot of times you'll see that like
that same problem, just looking at those points, right? It looks like you use co-location to match those points up.
Right. So we're actually going to get into the constraints now on how do you link those. It's not necessarily or inherently co-locating between them.
Yeah, you just basically constrain them to be equal to one another. The transcriptions, the dynamics transcriptions only act within each phase, and then connecting them up is just kind of equality constraints or inequality constraints. There's no dynamics at the junctures. That's why you can use the junctures between phases to represent discontinuous events like a discrete delta V or a planetary flyby.
Or an example for is like, let's say, as soon as this sail deploys, before that sails close, and then you're changing the dynamics, you're adding a sail in there.
Okay, yeah, whereas in a co-location method within one of those segments, it's ensuring that the dynamics that you've set up for that problem are like feasible throughout the trajectory.
Yes.
And it continues, but this could be discontinuous, and the dynamics could change.
Yep. Yeah, there's nothing forcing the phases that you add to an optimal control problem to be continuous unless you constrain them as such. So you could even have like a target phase in some orbit using some dynamics, and then a launch vehicle with different dynamics, and then that launch vehicle could deploy a low thrust spacecraft that then you just patch the back of your target in the low thrust, but the launch vehicle never has to touch. Yeah, it is up to you. You can transcribe as complex of a problem as you want, as long as you appropriately pose the problem and appropriately constrain what patches are required. Yes. Yeah, you as a user are expected to know the solution spaces that your phases should be using. Which I think is a good.
The phase for your Artemis and Gateway related work too.
Yes, yeah, we had that with some of the Artemis analysis that we did with Asset, where we had some Some models were pulling, spice kernel ephemerides for a target body like Gateway. And then we had one phase that was just our low Earth orbit and deployment orbit. So we had constraints to the front to tie it to what the launch vehicle could put us in. Then we had another phase that was, we have a finite burn engine, so we're decrementing mass and optimizing propellant usage. And then another phase after that, that's ballistic propagation in this, ephemeris model or CR3BP. So you can patch together a lot of complex problems with mixed solution spaces.
And these phases look, you're patching them together, I guess, and they look like they're connected in time. But
but they don't have to be. Yes, and we'll get
Yeah.
into that. Let's go through some of these link constraints and link objectives, and I think it'll illuminate a lot of the things that you're already.
HLS to Henry, HLS to Orion.
Stay tuned for the next section of slides for something very similar. Yes. Yeah.
So question on your integrating parameters do they have to be handled especially, or is it just a function of equating the two variables at the boundary?
Yeah, if you want continuity, you just equate them at the boundary. Yeah.
Yeah, we've even had an example where we had a known deployment condition or a known, primary spacecraft that we were going to be deployed from on a mission. So we could just integrate the path of the primary payload, and then we could set a constraint of our initial condition must start somewhere on this integrated path, and then optimize what's the optimal time to deploy from our primary to go out and do our secondary payload mission.
Yeah. I was kind of thinking of like for the entry problem I think you posed, you had like total heat.
Mm-hmm.
How do you have continuity on total heat, because it's an integrating variable, and you have to not only do you have to integrate it, but you have to alter the initial condition of the total heat
Yeah, so that's a good question. You can, it's not covered in the slides just for time. You can have, you can make the values of integrals of your phases equal to the static parameter. So you can basically, you can put integral constraints on something to say, I would like to take an integral over some function on this phase, like say the heat load, assign it to one of those static parameters, and then we can make all of those continuous in our different phases. So you can like kind of add different integration variables at the phase level rather than in your model, and then make sure those are continuous. And that's actually put in there for things like those integrated heat loads.
Okay, thanks.
Yeah, so that is doable.
So you just,
No, this is good.
you just mentioned something like starting with an integrator, and you just had to start from that point path on it. Is
Mhm.
that integrated path a phase, or is that just you do that and then you start anywhere from there?
How we formulated that is, so a phase, a good way to think of phases are a dynamic region that we want to optimize some input or some change of parameters to, subject to our constraints. So for an integrated phase, we have no control of it other than the deployment time. So in that case, we actually integrated the trajectory, and then just like the examples yesterday, we populated a 1D interp table with deployment time, so states and time of that trajectory is the lookup. And now we were optimizing the time that we used the lookup table from that integrated trajectory as our initial condition. And we were constrained that our initial position and velocity were equal to wherever that state was at on the integrated trajectory. Yeah, so it's not a phase. If phases are great for something where you have some level of control over, whether that be you have a problem formulated with a control vector and you're trying to optimize your pointing of an engine or a solar sail or something with control, or even a problem of I'm trying to solve for and find the initial conditions of a 3-body periodic orbit. I know this is constrained. I want it to start at the XZ plane of the CR3BP. So I've got that constraint and I want my X value to be this, but I'm going to allow the problem to vary my other initial condition states to create periodicity. That's a good use case for a phase, because even though we don't have a control vector, we can constrain some of the initial states and let the other initial states be changed and optimized by the phase. So if you have some kind of quote unquote control over that phase, even if it's not a control vector U, that's a good use case for a phase. But if it's uncontrolled, like integrated solution, then it's not necessarily a best use case for a phase. Yeah. So this is great questions and good discussion. So hopefully these next few slides will shed more light on this, on how this works, and then maybe spark even more imagination on how these can be appended together. So adding link constraints and link objectives. So we know with an individual phase how to add constraints to different phase region flags, like front, path, or back to that phase. Similarly, in an optimal control problem, we can add link equalcons, link inequalcons, and link objectives, where we have some vector function that we're evaluating. We're passing in some phase that's in the optimal control problem, along with that phase's phase region, and then the parameters that we want to pass to that function from this phase, and then a different phase that we're going through with regions that we pass in. So for example, we can do a add link equalcon and say, hey, we want state 0, 1 to be equal between phase 0 and phase 1. So we can take some function that's going to assess the difference between those states. We can say we want the last phase region flag of phase 0, the first one passed in, and we're going to hand index 0 and index 1 of our states to this function. Additionally, we want the index 1 phase from our OCP, so phase 1 here, and we're going to hand first, so the front of that phase, and we're also going to hand this function 0 and 1. So within this function, you can now find the difference if you wanted to constrain them to be equal and return that as an equality con. So again, driven to 0 by the solver. So that's a way to patch the back of one phase to the front of another. But there's nothing saying that you have to do back of one phase to the front of another. You could also say the two different phases start at the same place. So you could pass in a link inequal constraint or an equal constraint to some vector function. You can then do phase 1 and phase 2 and pass in the front of both of them and pass in whatever indices you need to that to add a constraint. So in that first slide, we showed the picture of a launch vehicle that then separates and has one phase that goes off to space and one that goes back and lands. You could do something like that where, okay, phase 1 is the upper stage that's going to space and it must start at some place, and then phase 2 is the first stage that's going to go land, but those components need to start at the same place, and then they're allowed to go to different regions and targets.
So this is also applicable when you're looking at constellations or you have multitasking.
Yes.
Yeah,
yep,
like if you
very
had
good
a
use case.
single launch vehicle that needed to deploy a constellation, yes, you could have, you're trying to figure out where does the launch vehicle need to insert, and then all of the different spacecraft will go to their different orbits.
Mhm. Swarm optimization, yeah, deploying multiple, separating into two different phases. Yeah,
You know,
definitely.
figure out what's the right time to do individual.
Yes. Yeah. Mhm. So we've got that ability that we went over of passing in phase region flags to different phases to a vector function that we instantiated. So you can do some kind of whatever mathematical operations you want on that. But there's also a lot of cases where you just want to enforce continuity between your phases, at least in some states or in all of your states. So there's kind of a shorthand way of doing that in the syntax. So you can take your optimal control problem and instead of add inequalcon, you can just do an add forward link equalcon, and you can pass from some phase in your OCP through some other phase. I want these variables to be equal to each other at back to front. So
Yeah,
this is
this is kind of the simple. In most cases, whenever you're just like trying to enforce continuity, it's just this one liner that says make all of these phases continuous in these variables. So this is something you should be familiar with, or you will use this a lot if you're trying to do multi-phase stuff.
Yeah, this will definitely get lots of use for anything that even if it's not continuous in all elements. So you're modeling, say, an impulsive burn where your spacecraft is flying out, then you do some impulsive burn at this phased linking region. So your first phase is coast up to where you want to do the impulsive burn. The next phase is after you've done the impulsive burn, you go fly out. You can do a add forward link equalcon from that first phase through that second phase and just pass in position and time, but leave velocity out. So now you're adding a constraint of, hey, my post impulsive burn phase needs to start at wherever my coast phase ended, but we're allowed to have velocity discontinuity because we're modeling an impulsive burn. And then say now you've got a discontinuity in velocity. Now you can say, actually, my objective function is minimize that impulsive burn. So you can say now add link objective, and then pass in a function that evaluates what's the change in velocity between the back of the first phase and the front of the other. And that's now you can return a normalized scalar. That's your objective function that you're trying to minimize, is that velocity discontinuity. So we'll get into examples of that that you will as users get to do tests of today. So this, yeah, as James said, this is a property of OCPs that you're going to use a lot, of just linking states between two different phases or multiple phases.
So in that case, would you have to put the function that does the difference inside one phase or the other?
No, that's applied at the optimal control level. So
okay,
yeah. So like phases are, you only do things. Yeah, you wouldn't try to do that inside of each phase. Like if you need to link things up, that's applied to the optimal control problem rather than to the phase. If it needs multiple phases, it has to go at the optimal control level.
Right. Kind of like a global variable or something like that.
Yeah, it's like globally organizing all of the different phases.
Mm-hmm. Yeah, good question. So once we've formulated our optimal control problem, all of these methods that you can call on your optimal control problem likely look very familiar. It's the same syntactical operations of what you use for phases to optimize or solve. You can just run it on an optimal control problem once it's fully configured now, and it'll solve this larger multi-phase problem all at once in parallel. So the example off to the right here is you've instantiated phase 0 relative to some ODE, applying whatever transcription you want for that phase and its initial guess and segments. You've applied whatever relevant constraints there are for just that phase. You do the same thing for phase 1 and phase 2. Here's the example that we were talking about. This ODE that you're instantiating from could be totally different solution space ODEs, or you could change different transcription modes between these phases. So once you've got all three of these phases configured with their appropriate initial guesses, transcriptions, and constraints and objectives, now we instantiate an optimal control problem object. We add all of those phases to, so best practice, add them in sequentially, because there's nothing necessarily constraining you to do that, but as a user, it's helpful to remember first in, first out type of methodology with your OCP. So we add phases to it. Then we can say, hey, we want range from index range 0 to 4 for all three phases. We want them equal. So add forward link equalcon from phase 0 through phase 2. So notice it doesn't have to be phases that are next to each other. This because phase 0 was the first one in, phase 2 was the last one in, we can do forward link equality from phase 0 through phase 2, and that means phase 0 is now going to be forward linked in these indices with phase 1. So the back of 0 is equal to the front of 1 in these states. And then phase 1 is also linked to phase 2. So the back of phase 1 is equal to the front of phase 2 at these states that we set.
So one.
Is
Yes.
that a
One is
function of
implied.
convenience? More so, could you be more explicit as to how you join it? I mean, especially if you wanted to like insert a phase or
Ye-
something like that.
Yes, that is a function of convenience, just because most of the time you're trying to enforce continuity between the phases and you got a whole bunch of them, so you just want to do it in a one-liner. But yes, you can absolutely go through phase by phase, and because I mean, as we'll see in an example in a minute, sometimes like the continuity between the phase might be like a planetary flyby, or you might if you have a launch vehicle and you're jettisoning some mass, you may want to be continuous in your position and velocity, but then you just need to add an additional drop off term in your link constraint for your mass. So sometimes you do have to go in and be very specific about how those links link up, and that link constraint can be any function, so it can be arbitrarily complicated. But yeah, this is just a function of convenience, because 60% of the time we just want to make a bunch of phases continuous in some of their state variables.
Yeah, it seems like you could get into trouble here with that one. So
Yeah, I mean, you can. It will, so long as it's like the indexes work out. It's like, you're good. Thank you for adding this constraint.
So what happens if I want to link phase 0 to phase 2 only?
You would.
You don't do forward link.
Yeah, you wouldn't do that. You would need to specify them manually.
Yeah, then you do link equal constraints and
Yes.
define a function for what you need. Yeah. And it's another useful note to this too, is you can have a single OCP can have multiple of these add forward link equal constraints as appropriate. So you could do, phase 0 through 2, all of them must be continuous in position, but then you could say, and if it's not happening in this example that we are showing the code for, but if there was an impulsive burn between phase 0 and phase 1, but there's not between phase 1 and 2, you could then say, okay, add another forward link equalcon from phase 1 to phase 2 and add velocity components. So now all of them are constrained to be continuous with each other in position, and phase 1 and phase 2 are position and velocity now, but there's still that velocity discontinuity between 1 and 2, and we can go on to say, an objective function or some constraint on the velocity discontinuity between these phases.
What's the range 04 in there again? I just forgot the syntax that you were showing.
Oh, that's just creating that you could, instead of doing range, you can just pass in a list of what indexes you want. Yeah,
Yeah,
that's
just saying
it's position only or position velocity.
Yes.
And then you could specify I want X and Z, but not Y.
Yes, exactly. Yeah, this is, we want the continuous, we want the range of 0 to 4, but you could also do a list and say, I just want index 0 and index 2 to be continuous. Yeah.
Yeah. Okay, because if I want XZ position, or XY position, not Z, and then velocity, you just specify 0, 1, not 2, 3, 4.
Exactly. Yeah. And anytime you see this indexing things with range, you could absolutely just use a list instead with the exact indices you want. This is just a shorthand of, instead of typing out everything in that range 0 to 4, we can do one smaller call. So
to give you and Jamie a chance to brag. So what's the biggest problem? How many phases have you guys had? And how many constraints have we had?
Hundreds or thousands of phases, millions of variables.
So how do you, you didn't hard code those thousands of phases.
Oh,
so,
no, yeah, it's generated in a loop.
Yeah.
Yeah, a for loop of spawning off phases as appropriate, and then you can link them all together.
How long does it take to optimize them?
It depends on what I'm trying to, I think the largest problem anybody solved was, I want to say that it was either Jared or Ari was doing something with virtual swarms, trying to optimize a probabilistic distribution of like phases with perturbed controls, and they had hundreds of phases. And that had in the millions of variables, and it didn't take more than a minute or two to solve.
Yeah, I was
Go ahead.
I was able to formulate an end-to-end outbound transfer for Artemis 3 with multiple different transcriptions. So it was tied to the launch vehicle. It had constraints with multiple finite burn, optimized finite burns with different changing engine properties as a function of mass. Multi-objective that then has the Earth deploy, optimizes 2 burns around Earth, does the translunar injection with a TCM, then does the close lunar flyby, and then in the ephemeris model and rendezvous with an NRHO in the ephemeris model. And that will optimize and solve in, less than 10 seconds, less than 5 on my laptop, not even a desktop.
Yeah, and as another example for GTOC 11, whenever we were doing the multi flyby tour through the asteroid, those problems had 70. We were doing like 25 to 30 flybys and using 2 phases per flyby because we want to have a maneuver. So 2 or 3 phases per flyby. So those are like 75 phase problems, and those were solving in less than a second. They were using it was 2 body, so we were using actually like a Keplerian shooting scheme, so we were able to keep the number of variables pretty small, even though the number of phases was really high. But it just it does scale up to a lot of phases, and like that was a highly constrained problem. We were having to hit like 30 flyby bodies.
Yeah, you can definitely build up really complex operations with these phases. And because we're interfacing with the vector function library, so we've got the analytical first and second derivatives, and SciOpt is written to handle and expect those analytical Jacobians and Hessians on top of asset being multi-threaded and properly vectorized in those packets 4 we were talking about earlier. You can run really complex problems really quickly. A very simple problem, I have had a use case where a really simple problem with just 1 phase or maybe 2 phases, I looked at the output of the terminal and it took almost equal time to generate the print to screen of the optimization run as what it took to actually solve the optimal control problem.
Well, I think there's a subtle too that, Jamie, that you mentioned, it's like you can generate this stuff, like you can auto generate the optimization problem, if it's of a certain type. And you don't have to go through and click through a GUI or hard code everything, because it's all in Python. You have that ability to generalize it and then auto create it, which is nice.
Mm-hmm. Yeah, there's I know we've gone through kind of the pain points of doing this in a programmatic way and defining your ODEs or defining your objective functions with these vector function arguments, but then the flip side of that coin is the advantage that you have, that all of this is programmatic. There's, you're not constrained to a GUI, so you're expected as a user to be able to interface it with it in a programmatic way, but then you get all the benefits of solving optimal control problems in a programmatic way. Yeah, good point.
It saves development time.
Yeah. So that was a definitely a good setup. So how do you get these optimized solutions of anything from something that solves faster than what it takes for your computer to actually print something to screen versus solving millions of variables in less than 10 seconds? It's the same method calls that you ran on phases, you can also run for an optimal control problem. So once it's formulated, you can run optimize, where again, it's going to take whatever your total objective function is. So it could be multi-objective and you're summing the objective functions and their weights. Minimize your total objective subject to all of your constraints. That means the constraints applied to the individual phases and any link constraints between your phases, and optimize that so that you satisfy your constraints and minimize your objective functions. Or if you just want a feasible solution, you can run OCP.solve, and then again, these other convenience functions are there still too, of solve, and if solve it, then optimize it, or solve it, optimize it, and if optimizer fails, at least solve to get back to feasibility space, everything like that. Then once you've solved your OCP, remember, you could do OCP dot phase and pass in a phase index to return trajectory. But remember, the phases that we added to the OCP are the same object. So once you've run OCP.optimize, you can get the optimized trajectory from the individual phases straight from the phase itself .return traj. So you don't have to access phases through the OCP. You can just pull the phase itself and do return traj, and you're getting the trajectory that's part of that entire optimal control problem. Similarly to how, again, this is probably looking familiar, it's that reuse of syntax and operators. So just how in a phase, your phase creates an instance of an optimizer member variable that you could change settings for, your optimal control problem does the same thing. So you can now have access to optimizer settings, like do you want line search, change the line search mode or iterations on line search, you can change the print level. And you can do that for the optimal control problem itself also. So again, see the tutorial, because these number of user settings for optimizer tweaks and changes are pretty extensive. So let's do an example. This is going to take that same problem formulation that we've seen for all these other examples and add a little bit more complexity and solve it in a way that requires multiple phases. So we are trying to do a mass optimal low thrust transfer that now, instead of just the low thrust transfer from departing body and arrival body, there's a red body here that we can do a flyby of and then go out to the blue arrival body. So depart from green, do a flyby of red, and then arrive at blue. So again, we're going to have bounded departure. So there's some V infinity that you can't exceed from the green body. We're getting launched from the green body, but we can't obviously have infinite launch energy. There's going to be some constraint to how much velocity discontinuity our initial condition can have from the departure body. We want a full rendezvous with the target. So at the end states, we want to have position and velocity continuity with the arriving body. We're going to bound the throttle vector of our low thrust formulation again, so that again, the controls don't exceed what we've actually built the engine model to do by going magnitude greater than 1, and it doesn't do weird math of trying to make your control vector magnitude 0 or less than that or anything. Then we're adding a mass optimal. So our objective function is going to be minimize the integration of our control vector for the whole transfer. So we're going to use an impulsive flyby approximation. So we're going to do a flyby of this body, and we're going to do a constraint where we've got discontinuous flyby. So this flyby point where we are arriving at the body and then departing the body with a flyby is going to be discontinuous. So we're going to have one phase that goes from departure body to the flyby target, and then another phase that's after the flyby out to the rendezvous point. So again, we're going to require the 2-body ballistic ODE and the 2-body low thrust ODE that we've derived and talked about pretty extensively yesterday. So we're going to set up a similar setup to those previous examples where we've got our parameters that we set up, like the V infinity limit, the throttle for our initial guess, engine properties, gravity of that central body that we're all orbiting around. We have initial conditions. Now we have 3 initial conditions, the departing body and arrival body, but also a flyby body that we can do as an initial condition. And we're going to instantiate the ballistic 2-body ODE and the low thrust ODE, and then of course get associated integrators with each of those. Notice once again, we're using that tangent control law for the low thrust integrator. So now any solution we integrate in that solution space with that ODE, we'll apply the tangent law to our control vector. We now, because we have the integrators and we have the initial conditions of all three bodies, we will propagate them out using the integrate dense call. And once again, we're going to load all of that integrated trajectory data into 1D interp tables so that we can do a smooth fit of those discretized and integrated points. So this should feel very familiar, except we've now got this intermediate flyby body. So we've got, supplemental things for the initial guess generation. We could use a Lambert arc search or Lambert search for targeting the flyby body and then flyby body out here, but we've just got integrated solutions. So we're doing this search that flies through and goes from departing body to the flyby, and then a second one that goes from flyby body to arrival. Again, you were sent with the meeting invite, there was that directory, that zip file in the directory. If you unzip that, this is still in the day one section of that. The code for all of this, along with these slides, should have been delivered.
Not having looked directly at that yet, which I will, but so does this then ensure that the incoming and outcoming the infinity are the same for that flybody?
We will. Right now we haven't yet.
Yeah, the problem we're about to solve does this. Our initial guess is just trying to get us something that's roughly going to be in the ballpark of that. Like that search is not the way you should do this. That's why it's not shown here. There are better ways to do that. But it was just it was another example of using integrators to do it. It's not how you should do it, but it just gets us something close here so that we're in the convergence radius of the optimizer.
Yeah, but then once you do the optimal problem, have that in there.
Yes, and we'll see those constraints here in a second.
Okay.
Yeah, so yeah, this is still just the initial guess generation. We haven't interfaced with phases yet also, because each phase needs an initial guess trajectory. We still need those for patching those together. So this is a way of generating these black dotted line initial guesses. But now we'll move into, as you talked about, setting up phases and any relevant constraints. So phase 0, this is the phase that we're saying we're leaving from the departure body and going out to the flyby body. So phase 0, we're instantiating from the low thrust ODE. We add our transcription method, the initial guess that was generated in the previous slide, and then some number of segments. Then our first constraint is we're going to add an upper function bound to the v infinity function. So this is the exact same v infinity function that we showed in yesterday's phases tutorials, where we are passing in, this is constrained to the first or front phase region. So just the initial condition of phase 0 is subject to this function defined over here, and we're passing in the interp table of the departing body. Then it's expecting size 4 arguments. So we're going to give it velocity x, velocity y, velocity z, and our time, our initial time. And then we're going to constrain it to some v infinity amount. So within this vector function that we're adding the upper bound to, it breaks apart our velocity and time vector functions, and we are just returning the norm. So the magnitude of the difference between our velocity and the velocity of the departure body at the lookup time. So we're passing in, remember, we've got the departure body table, which if you hand that departure body table time, it returns position and velocity of that body at that time. So we pass that into this. We're also handing in as a vector function argument our phase time at the front, so our initial time. And so this RV tab passing in t is going to return what is the departure body's position and velocity at our initial time. We're only looking to do size 3 because we're doing a difference in velocities. So that's why we then do the dot segment 3, 3. So this is pulling out just the velocity of the departure body at this time, taking the difference between our velocity and that departure body velocity at time. We're going to do the norm. So it's just a scalar magnitude velocity difference, and it's constrained to v infinity. So this is exactly the method we showed for the phase yesterday, where we had some constrained V infinity departure. I get skipped a section here. Not letting me go back in time. Let me pause.
What section do you think is skipped? I think the image just got shifted.
Yeah, sorry. Departure phase, V infinity. Okay, there we go. Sorry. Slide. Okay, sorry, we're up and running again. Technical difficulties on my side. So we've constrained the V infinity for this phase 0 for our departure. Now we're adding a position constraint. So for the front, the start of our phase, we want continuity with the departure body in position. So again, we take this position constraint and pass in for the first, so our initial conditions, we're passing in the departure body table and handing it our position X, Y, Z and our initial time. This is breaking position and time apart for our phase and computing the difference between R and V, or sorry, R and the departure body R. So again, this departure body table lookup at time gives us position and velocity. So that's why we do head 3, so that we're just doing R of our state at initial phase. So first minus the departure body. So I know I did this exact quiz yesterday. What size is the vector function that's being returned by this? Yes, it is size 3. So we're adding an equalcon to something that's returning size 3. So that equalcon is going to try to drive all 3 elements to 0. So if the difference of these vectors are driven to 0, that means X, Y, and Z are now constrained to be equal to the X, Y, and Z of our departure body. So we don't have to do a scalar operator on this. We can do vector operations even in the constraints.
Right.
Yes, so in V infinity, so the previous phase, we had a norm constraint. So we were returning a scalar because we don't care about the angle of that V infinity. We just cared about the magnitude to make sure we don't exceed it. So in that case, we could just do a norm and do a scalar. Here, we want continuity in all 3 components of our position. So we are just returning a size 3 to this equalcon. So all 3 components will be driven to 0. So now we've got our initial conditions constrained on this transfer from depart body to our flyby body. Now we need the arrival conditions constrained because we want to obviously target our flyby body to go do the flyby. So we can now add another equalcon, this time using the last or back phase region flag. And then the rest is almost exactly, or is exactly what we did for the departure body, but now we're handing it the flyby body table. So now the initial conditions are going to be constrained in position and time to be at where the departure body is. And now the end of this phase is constrained to end in position where the flyby body is at that time. Change slides. Sorry, technical difficulties. Okay. So stop here. Move on to slides. Start from this slide. Okay. We're back. Okay. So we've constrained the initial conditions of this phase and the terminal conditions of this phase, but we're also trying to solve an optimized problem, not just a feasible problem. So we said we're integrating the magnitude of our controls as our constraint. So now we can do for this phase, add an integral objective of some argument size 3 and the norm of that, and we're passing into it the index 7, 8, 9. So we're passing in the control elements. You could, this is kind of a shorthand way to do it. You could, if you're more comfortable with it, write a vector function that you instantiate here, but since there's just a single operation, we're doing the integral object or integral objective on an arg size 3 norm and passing to that arg size 3 the 3 control components. So we've now got all of our initial and terminal constraints and our objective function added. So what we have left to do is add some constraints to the performance of what the vehicle's doing. So for the entire path, we want our controls to be constrained between 0.001 magnitude and size 1 of weight 1 on this constraint. So we do the LU norm bound. So that sets our path for the entire path, have set it for that vehicle to not exceed our control authority. So we finished the phase going from the departure body to the flyby body. Now we're going to instantiate a second phase. So phase 1, again, we're going to instantiate it from the low thrust ODE because we're still our spacecraft. We set our transcription, the initial guess that we had for the post flyby state and its segments. Now we're going to once again constrain the control to be bounded and in magnitude between the bounds we expected, add the integral objective to this as well. So notice we've got 2 phases, both have a objective function to them. But remember, when we configure these into an optimal control problem, the OCP can be multi-objective. So it will add the integral of your control usage in phase 1 to the integral of your control usage in phase 2. So the overall objective function of the OCP is your total integrated use of U.
So what was the rationale for not having 0? There's like a divide by 0 somewhere? Or?
Yeah,
it's undefined. Have you ever heard of the concept of leak mass?
Of what?
Leak mass?
Leak mass?
Yeah. So like, if you're trying to like, well, first of all, one of the reasons you do it is we're taking the integral of the control here as our objective, and so we've got to take the derivatives of the norm of U.
Yeah.
Well,
okay,
what are the
okay.
derivatives of the norm of U? It's 0. It's infinite. So you literally can't have it be 0. And you see a lot of times you'll like in tools you'll see them talk about the leak mass. You typically, to handle problems like that, you have to say that the engine can't be totally off. It's just something really small. We could set this to be smaller. We just did 0.001 here.
No,
Just
right.
yeah. You
But
could
this
make
kind
it
of goes back to
arbitrarily
runback
small. It
versus
just
0.
can't be 0.
Yeah, right. No, okay. I just was curious as to where that.
Yeah.
I figured it was a divide by 0 somewhere. So that makes sense.
Yeah, that's it. It is.
Yeah, because we're doing a norm call, so we have the absolute value there. And since we need the second derivative, so you can go lower. I've used for some engines where we're doing a thrust 1e to the -12 or -16, just something so that you're not using absolutely at 0 where it's undefined. So good point, good question. So we've got our controls constrained and set up. Now we're going to add an equality constraint to the final body, or to the final point in this second phase. So using last or back, and we're going to use that same rendezvous constraint that we talked about yesterday, this time passing in the arrival body table. And notice we're passing in position, velocity, and time because we want a full rendezvous. We want to show up at the arrival body in position and in velocity at whatever the arrival body's position and velocity is for time. So this constraint, this rendezvous constraint, is size 6 now because we're returning vector a vector subtraction of the position and velocity from the position and velocity. So it's driving all of those with the equalcon to be 0, so that at the back, at the last phase or last point in this phase, we need to be continuous in x through z dot with the arrival body. So we have the phases set up of departure body to arrival departure body to flyby, and then flyby body to arrival. So this is obviously a multi-phase problem. So we're going to construct an optimal control problem object. So set up an OCP with the call from optimal control. We're going to append those phases into it. And now we want forward link equalcon. So we'll just do a pop quiz since we're getting close to, writing these on our own. What is this call, this forward link equalcon constraining between these phases?
The first, second, third, and seventh states to be positions.
Position
Yes.
and time.
Yep. So we are enforcing continuity between the first phase and the second in position and in time. But notice there's not continuity in velocity. So this is satisfying its constraints as long as these two phases are continuous in position and time, but it allows for a velocity discontinuity between them and still meets its constraints. That's because we're doing we're emulating a discontinuity in velocity for a flyby with the arrival body. So we want to constrain that, because if we don't constrain that, we're not actually representing some flyby, we're just representing some velocity jump or discontinuity. So the next step is to take these regions, these states that are not constrained to be equal, and set some value constraint to them. So we're adding a link equalcon using this v infinity match constraint. So Will, you even hit on that already of, are we going to represent the v infinities? Because your v infinity coming into a flyby and leaving one had better match if you're doing a ballistic flyby. So we're using the add link equalcon method. We're first passing in the function that we're doing this for, this v infinity match function, and we're passing in the table for the flyby body. So now notice this function is expecting size 8. So then we've got the function defined. We then say, all right, we're going to hand it phase 0. We're going to do the last phase region flag for phase 0. So the final point in phase 0, we're going to give the velocity x, velocity y, velocity z, and time. And then for phase 1, we're going to give the first. So the front of phase 1, we're also going to pass in velocity x, velocity y, velocity z, and time. So that's why this function, even though each of these looks like size 4, we're passing both of these in, one from each phase at different phase region flags between them. So this function needs to be arg size 8 because it's getting 4 from front, 4 from back. But this initial x that all of these args are, it's getting handed in wholesale, all of them. So next we want to split them out. So velocity of phase 0 is going to be head 3. Time of phase 0 is going to be x of index 3. And then velocity 1, we can grab, you could do, again, we showed extensively in the vector function section, there's a bunch of different ways you can slice it. In this case, we can even say, we want size of vector tail 4. So give me the last 4 inputs into this function, and then do head 3 on that tail 4. Or we could do a x dot segment and do start at index 4 and do size 3. However you want to transcribe this, as long as you're allocating the proper inputs, you can pull out velocity of phase 1 at this path point and time. Then we can simply just compute the v infinity at time 0 and time 1 relative to the velocity of the arrival body. So we're passing in the table, the 1D interp table of the flyby body, throwing in the times that we're encountering it at and computing its velocity, taking the difference between its velocity and ours, and then the magnitude. So we now have the v infinity of the body that's arriving at its last point in the phase, and the v infinity relative to the flyby body at the front or first phase of phase one. So now we can just return the vector difference, or the scalar difference between those, because we did norm here, so these are both scalars. Take the difference, and because it is a link equalcon, it'll have to drive that to 0 to satisfy our constraints. I want to give enough time and make sure, did we lose anybody on that? I know this was the first time you're seeing this kind of complexity of doing operations within this function, passing in different arguments, but is it clear that this is now a phase that's constraining it, that we have a propellantless, or a burn-free flyby that is enforcing a continuity of the flyby? Perfect. So then we've just got one more thing we wanted to add to the body, or to this problem, and that is, if you do a flyby of some planetary body, it's going to produce a turn angle, right? From your heliocentric frame, you get some turn angle. Right now, we've said, all right, v infinity needs to be equal at this patch point of our phases, and position and time needs to be continuous, but we haven't really constrained what the maximum turn angle is. So to represent this impulsive flyby, this flyby approximation, we're going to add an inequal constraint on a function that's the flyby angle bound. So we can change how much is this flyby allowed to change the angle of our velocity at the back of phase one and the front of phase two. So we're going to call this flyby angle bound function, and we're going to pass in the lookup table of the flyby body, that same 1D interp table. We're going to pass in the flyby body's gravitational parameter, and then the minimum radians angle constraint that we want to apply. Then once again, we're going to pass the final phase 0, but this time we're passing in velocity as well, velocity and time from final of phase 0 and from first of phase 1. So we're passing in the interface between these phases. So again, this is argument size 8, because we're passing in 4 from phase 0 and 4 from phase 1. There is nothing necessarily dictating that these be the same size. I mean, this specific problem requires that, but if you had some constraint that needed a different amount of inputs from 2 different phases, there's nothing stopping you from doing that as a user. I might add as a note. So within this problem, we've now passed in our 8 arguments. We're going to partition them apart to get velocity 0 and time 0, velocity 1 and time 1. We're then going to compute the v0 and v1 directions. So we can take the table lookup, get its velocity, and subtract our v0 and v1 from that, and then normalize it so that these are just unit vectors. So these are our flyby body relative velocity vectors. So we've now gotten the velocity relative to the planet for both these phases and normalized it so it's unit vectors, because we're doing an angle constraint. We don't really care about the magnitudes here. So v infinity 2 function here, we're going to take the v infinity squared. So we take our flyby body velocity, subtract off our approach of our v infinity and squared norm. So we're normalizing it as a scalar and then squaring it. And then we can do a delta of our arc cosine of the dot product between our 2 relative velocity vectors, then set a delta max. And that delta max, we're going to need 2 times the arc cosine of, these are all, this is not an asset specific thing. This is essentially just taking the 2-body flyby formulation and finding what's the maximum change of turn angle a planetary body can produce. So we're constraining relative for this body with its mu value, with its gravitational accel, and our minimum constraints, we are setting what's the maximum turn angle you can set. And then we're simply going to return the difference between the turn angle that is produced between our phases subtracted by the maximum turn angle. So we're setting an inequality constraint now. So this function that gets returned, an inequality constraint, is bounded to satisfy this constraint must be less than or equal to 0. So if our turn angle that we compute, delta, is ever greater than the maximum theoretical turn angle, this function is going to return something greater than 0. So we're in the infeasibility region. But if we are equal to the maximum or less than the maximum turn angle difference, this link inequal-con is satisfied.
So the dynamics that you set up with your problem won't ensure this already.
We're using just regular two-body, so the only active gravitational mass, as far as most of the dynamics is, or as far as the dynamics are concerned, is the sun, and we're just assuming, you know, this is a fairly common way to do it. Is you just kind of ignore the flyby body until you reach its sphere of influence, which you assume is really small, and then you just apply this flyby as using this constraint. You don't actually do like an in-body simulation. If we had an in-body model here, in principle, yes, you wouldn't have to add a constraint like this. It would still be, that would be a super sensitive problem, very hard to solve. But this is a fairly well-conditioned way to approximate the flyby.
Gotcha. Makes
Mm-hmm. Yeah. So you totally could do it as an n-body, right. But it's
in physics, like but since you're not modeling gravity, it could tell you I'm going to turn this way because there's nothing about the body itself saying that it will maximize have that constraint.
Yeah. So that's even another example of asset as a general purpose optimizer with astrodynamics utilities. You can formulate whatever problem you want to. So it is partially, I think, as it should be and as it's appropriate, it's on the user to make sure you're formulating proper problems. There's not every problem is a nail, so we don't want every solution to be a hammer.
Possibly super technical two-part question.
Okay.
Maybe pay attention. When you have two boxes of something, right?
Mm-hmm.
This goes back to something I've been struggling with for a couple of weeks. In the box on the right, you defined, not in the box, but at some point, arguments, like optimal control arguments of a certain vector size. So if I'm going to guess right, it's 6 vector, 7 vector, because you have time in there. Cool, right?
Mm-hmm.
So you have like args or whatever you did equals OC.arguments, and that doesn't do anything besides return what C does. That's your interface between Python and C that basically creates placeholders for those variables so that the C code on the other side knows what that is. So then you come over to your flyby angle bound and you say, cool, well, X equals args 8. Args 8 has nothing to do with the other arguments, right? Mm-hmm. Now, obviously, those variables are the same in some ways, right? They're not necessarily the same references per se. They could be. So the question is, how does the C code on the backside delineate from these being either similar or separate? Because you're creating another set of variables. And like in this case, it's kind of different because you have velocities and times, right? So, but you're looking at specific points for those. But if you had an argument, like if you want to do something else, how does it know when you hook it in through the C code that V0 actually would correspond to the velocity over on the other side, or if it doesn't?
That all happened.
And then the second question is, given that this could be, because you could do this a lot, right? Because you could have multiple ways to do this. You have multiple instantiated different chunks of arguments. How do you keep them straight as a convention that you guys have dealt with? Because you could have multiple ones of these, these vectors floating around, and this one's this size and this one's this size, and without looking at it, you've kind of applied this when you've asked how big is the vector that we're returning, right? Do you guys have a convention which kind of makes this more obvious so you don't hurt yourself?
Yeah, I mean, the logic of like what variables are going to get passed in is defined right here whenever you add the Lincoln qualcon, because we're just trying to hook up, all right, which variables in this phase actually need to be passed in what order to this function. These args don't have to know about our ODE arguments or anything like that,
Okay.
because under the hood, this is just a shorthand, or this is just a way to tell the optimizer under the hood, send these variables to this function here on the left. They don't have
So,
to know
yeah,
anything
so-
about
so-
each other.
Instead of reading the arguments definition as the quote unquote inputs for C, because you're putting the holes there for C to know, you're still doing the linking on the inequality side.
Uh-huh.
Because you're still manually linking it so that when this all runs, then it figures out, oh, well, this bucket goes to this bucket, and this bucket goes to this bucket, and then you're kind of linking them together.
Yeah, I mean,
that way.
think of this
Okay.
as kind of like a format string where you write out the format string and you leave the actual variables free, and then you say dot format, here they are. That's kind of what this
Gotcha.
is doing.
Yeah. So then it goes back to your initial answer that you gave us like 2 weeks ago. That args basically doesn't do anything.
Yeah,
You're doing.
it is syntactic sugar for setting up the like computational graph.
Right. I mean, it's something because you have to have something there so that Python can bite on it. You can write the rest of the equation, right? And so,
Right.
yeah, I see. So then,
Yeah,
in terms of the convention, so how do you guys do that?
I
So-
mean, what do you mean? How do we do that?
Well, I mean,
Right,
you potentially, because you have like you mentioned that you've had like hundreds of phases, and each one of these phases could be different sizes and different, variables. I mean, there's nothing to stop you from doing that. How do you keep track of, or how do you document which ones are which size so that you know it without staring at the code going, oh yeah, this is only 8. Duh. To bring up a sore point, kind of like when you added theta into the VR4BP stuff, and you're like, oh yeah, time moved, ha ha ha, silly me. How do you guys do that and handle that? Because there's nothing at the asset level to prevent you from hurting yourself, right? And that's fine.
So as far as like moving indices and stuff, yes, that is all just kept track of by convention, or not.
Well, right, but what's the convention?
I mean, it's the model, the ordering of the models. So like the way that we order state variables coming in, and the time derivatives coming out, you have to obey that order. As far as what you're talking about, where you add another state variable and time changes, yeah, you just have to keep track of that. Now we do have an update.
Like the fly by angle bound is a good example, because you have again 3 V's, a T, and then 3 V's and a T, right?
Mhm.
That's not what you do over on the other right hand box. And so, granted, this is a special situation, and so you're probably aware of it a little bit more than normal. But like if Aaron were to give this to us and throw it over the fence and say, cool, we get this, short of going through this line by line and going, oh, this is exactly what he's doing at all times. Do you guys have a convention where when I'm putting this thing together, go, oh, I know what numbers that I need to use for these indices for these, so I don't do something silly and then go, wow, look, we flew all over the place. That doesn't make any sense. Then I have to go find Aaron who's available.
Yeah. So right now, the answer is no. There's going to be an update in a few weeks, perhaps less, where you name things rather than by indices, by strings, and then you can say, all right, I would like to connect position in this phase to position in the next phase, and then the indices are not visible to the user. They don't have to worry about what they are, so long as it's like, as long as it makes sense to link to position, which of course it does, and you've named it the same in each different model, then that'll all just work transparently.
It becomes a little bit more transparent and more explicit.
Yes,
but again,
that is coming. Like that's actually already complete. Just have to write the documentation for it and get it pushed to master. It's already there. It will eliminate all of the usage of indices here. That will always still be an option to use the indices because that's the underlying implementation, but we will be hiding that behind string naming so that a lot of this is more clear. So in the end, this thing would say fly by angle bound. I need the velocity and time from phase 0 and the velocity and time from phase 1. Pass that to that function. That's a lot more clear than what reading the indices.
Which again is instantiated in your ODE definition. So like we said yesterday, you could write an ODE
for whatever reason, in whatever wonky configuration you want, where
Yeah.
index 1 and 2 are X and Z, index 3 is mass, index 4 is Y.
Right.
But writing your ODEs in consistent format of, okay, I'm going to do position, then velocity, then mass and time. Now you at least know, okay, I have written my ODE to be the first 3 are position, the next 3 are velocity. So you at least know you're passing it when you're passing things to a vector function argument. You know, okay, if I need position, I define my ODE in this very sensical way where position is the first 3. So I'm going to pass 0, 1, and 2 to pass the first 3 in.
Right, but it's still on you to know that. That is.
It is. It is.
Yeah.
Yeah.
Yeah,
And
but
also, if you decide
but
to
Ben,
break a
that's-
convention, swap things around,
Yes.
with this
Yeah.
new update, you could hose yourself. Because
Yeah.
you might end up
Right.
with different, because string convention is gonna assume position first and velocity
well,
next.
it's not going to assume it. You're going to set it to whatever you
will-
want,
you can
and
set
then
it
so
once
long
at the
as
beginning.
people have named position the same and different things,
So you-
it'll just
yeah,
work.
so you
Okay,
can
so
say
you're gonna
position,
specify.
You once again in your ODE, just how in your ODE you get to choose what convention for your states are. You can change
specify
convention for these.
position equal to indices 1, 2, and 7.
Yep.
And then position will always
Be
indicate
1,
those.
2, and 7. So
Yeah.
So it takes out some of those guesswork.
Yeah.
And it's not so much for me as the person writing the code, right? It's the, hey, I'm giving this to someone else. Hopefully they understands all
Yeah.
the things that I was assuming, right?
Right.
But no,
Yeah.
Ben, you're exactly right. This is one of the things we identified as a pain point for people passing code back, because the person using it always knows what convention they were using it, but exchanging was really might make things confusing. That's why we're doing this string thing. It will, like I said, it wasn't quite ready to make it into this training materials. Everything in these training materials and this convention right here still valid, still a way to do it. But we do have something that's going to clean up a lot of this coming, and you can mix and match. It'll be very easy to transition from this to the new thing. It actually doesn't break anything. It's all just a new ways of doing stuff. And that is to address exactly what you're talking about, readability. I mean, like, okay, he made position this, he's linking his positions here. I don't have to worry about these indices.
Cool, okay.
And if my
And-
model, if I'm trying to interface with him and I made my model differently, so long as we both name things position, or so long as, I know what he called position and here's what I called position, and those do correspond to one another, I can say these need to be equal.
And that's again, similar to how Asset doesn't have a GUI, it's a programmatic approach. There's that trade-off between knowing your own, establishing your own conventions and sticking to them, or, we'll get on later to some pre-built models from the Astro library, but those are coming pre-built. So since you aren't defining the ODE yourself, you're now taking on the pre-built conventions that model's built with. So there's, for any tool, the more finite, there's pros and cons, and the more finite you are in establishing the physics, the more you have control over the convention versus, taking a tool with a GUI and hitting run. You don't know if it could be a black box to you and you get results, but now you may not even be aware of what convention assumptions are being made under the hood to produce the results you have. So it's always an option to you to use these pre-built models with their predefined conventions. Definitely.
Good question.
No, it was a good one. Good discussion on this. So yeah, it's a good idea then also to practice, similarly to how in your defining your OC or your ODEs, your solution spaces, you set the convention for what things are in what order. You also are, if you think about it, setting the convention of how this vector function, any vector function you define is going to be just handed some argument size structure, and you are setting a convention on, okay, I'm breaking this structure apart in this order where V0, velocity 0, is going to be head 3. So whatever I do on this side, whatever convention I use on this side, I need to make sure the first 3 arguments I'm passing to this arguments instance are velocity 0, because I know that's the convention that was written, that I wrote as a user in this function. Yeah. So that was good discussion. And that was also our last link constraint we needed before we can solve this multi-phase problem. So we've got, as a quick recap, we've constrained our initial and terminal constraints for both phases. We've found a link between them. So the phases are continuous in position and time. They are discontinuous in velocity, but we've added equality constraints so that the v infinity vectors, the relative velocity vectors of the flyby planet, when they both do that position where they're doing the flyby, are constrained to be equal to each other, and we are doing an inequality constraint to make sure that the turn angle that this flyby is producing is realistic to the physics of the body we're doing the flyby of. And we've set our constraints on the norm of the controls and added 2 objective functions, the control integration from phase 1 and the control integration of phase 2. So we've now got this full configured problem set up, so we can run optimize on the optimal control problem itself to optimize this whole problem in tandem, this multi-phase objective, multi-phase, multi-objective optimal control problem. And then when it's optimized, remember, these phases that we've appended to the optimal control problem, these are the same objects. So to get what is my optimized trajectory from departure body to flyby, we just take phase 0 return traj, same thing for phase 1. You could absolutely also do OCP dot phases index 0 and index 1, because that's also going to point to the same object. Yep. And you'd get the same output. And the result of running that is, one, as we've kind of hinted at with the fun of this, you optimize the problem in less than 1 second of runtime, so extremely fast in solving this. And all of these things that we've been building up towards, you've now created a low fidelity approximation of the Psyche trajectory. So using a flyby from Earth, doing a Mars gravity assist, and then flying out and arriving at Psyche. So that's what we've been building to in all of these incremental exercises. And you have this code delivered with the meeting invite if you want to pick through it or need to look back in detail at some of these. So I don't know if we looked at thrust levels, and we've non-dimensionalized
Yeah, so
it. So
this is so like Psyche actually has a pretty, fairly high mass, like their mass fraction is pretty high, so they're actually getting a lot more. You can't approximate Psyche's trajectory as just a constant acceleration like we're doing, so it's not quite exact, but we're using roughly the same acceleration, the same start window, just to show that you can pick out the right launch window and get a low thrust transfer. We need a lot higher fidelity thrust model to really get this to match up exactly. So like they've got like forced coast checkouts. You could put more phases in there to do that, but this is just a low fidelity approximation.
So again, maybe maybe another physics question, but kind of related to this, I guess, is that there's a possibility that flyby might not work for your launch state, or that a different flyby might be better. Is there, what would the process be, I guess, to say, do this, but also do the non-flyby option and find the optimal or other flyby options and do the optimal of all of that?
yeah.
The non-flyby option was actually the example from the last set of slides.
Right, but I'm talking like in one problem, right?
Yeah. Oh, in one problem? Yeah, that would be, I don't know if you could do that necessarily in one problem, or I don't know if you'd want to, because would you be like trying to, unless you were trying to constrain your different options to have the same launch date.
Right. Well, yeah, that's what I guess I'm getting at. Is like I want to get from here to Pluto. I have all the planets at my disposal. I can do a 20-year, mission if I want. It's very open-ended, right? It could be any launch state, but like I don't know that I want to use Mars. I might want to use a different planet. and I want to see what the best planet is to do the flyby, right? Or if that a flyby is even necessary within my, dynamics.
Yeah, you
But
can't really do like optional constraints and things like that in like a gradient based optimizer. It just doesn't work very well. So in that case, you would have to, for each type of configuration you want in, like, say, this architecture, you would, all right, formulate the Mars flyby problem and then test that. Formulate one that was Venus flyby or Jupiter flyby and test that one. There's no way that you could like incorporate that into one problem that you hit optimize on and it's going to figure out, because that's getting into like a multi-objective, like discrete choices, and that's outside of the bounds of this particular optimizer. You certainly use asset as the inner loop of something like that that's going to try to apply some heuristic to figure all of that out, but it's not something we can set up as that type of thing is not something you can set up as a single optimal control problem.
Yeah, each configuration of that potential mission makes for a great optimal control problem, but appending them all into one massive optimal control problem is not maybe the best approach. But you could definitely, because it's programmatic, you could programmatically configure use a Lambert solver to configure initial guesses to each of those bodies, and then have programmatically it loop through of, all right, here's my initial guesses of how we've generated Earth to Mars to Psyche versus, Earth to Venus to Earth, and programmatically approach that, forming different OCPs.
Something like that.
right, that's what we like. What would be,
And you still got kind of wonky results in certain areas. So
sure. Okay, thank you.
Yeah, good question. Good formulation of an OCP is often one contiguous configuration of a mission.
Not great one set up with this stuff.
Yeah. But, as you saw here, this optimal control problem solves in less than a second. So you're not going to take a computational hit if you want to do a solution search of different configurations, which Asset's GTOC 11 paper shows, solving a lot of different problems very quickly to compare those.
I think we did we probably did in the tens of millions.
Yeah.
That function over it was
Yeah.
No,
but that's the thing, is like so that's fit in the option, but then if you start thinking about like what's like, you could go Earth, Venus, Earth, like, or you can multiply. There's like an infinite number of flybys you could do.
Well,
As opposed to just
right.
bouncing around to permutations that the planets, right?
I limited to like, if you're going in one direction, like, you could choose any place in between the two planets, but you wouldn't go inbound. Because then you could just go back and forth, back and forth, back and forth. Right.
Yeah, definitely. Definitely as a user want to make, this is a tool for astrodynamicists. It's not a replacement of astrodynamicists, so.
You don't have the.
You need the
Yeah. No, I mean, like all of those existing, like really cool multi-planet search algorithms that like JPL and develop, like those. This is not a replacement for those. Those things are awesome. Like they're built exactly for that type of problem you're describing.
Right. Yeah, that's what I was getting. It's like the programmatic level mandate of go here, push button, what optimal, But,
yeah, I mean, you'd have to. I know. Does EMTG do something like that?
Could you say that again, James? Sorry.
Does ETG or is it EMTG? It has some sort of globalization loop, I think.
Yeah, it's definitely a good trade study tool.
Doesn't EMTG use SNOP though?
It does.
It does.
I mean, last I was checking.
Okay, so this was good discussion. I hope this also helped kind of formulate in your mind the use cases of optimal control problems and any relevant bounds on it or constraints to it. Again, I feel like I'm said this a few times, that's also another advantage of having asset as a programmatic tool where you're writing it out is you're absolutely free to write functions to spawn off phases as you need. You're not constrained to like a GUI interface of, all right, I'm locked into this architecture as I've added phases to a mission or anything like that. You can programmatically generate phases that get appended to problems to resolve, or copy a mission. Yeah, copy a mission and modify that phase and then resolve the optimal control problem with different constraints added or dropped, or entirely more phases added in or phases removed. So definitely can be worked as an iterative tool also. So conclusion, once again, pointing towards the tutorials online. There's also a designated section in tutorials for optimal control problems. So each of these first 4 slide packets that we've gone through has their own tutorial section online in the documentation that walks through in more detail and has a lot more extensive overview of all the things that are exposed to the user, including things we just didn't have time to get to today, like the instantiated member function optimizer settings and tolerance changes, things like that. Yeah, that's a good idea. So let's even kind of open that up because we're not quite at, or we're at the end of this slide section here. So let's do a live demo of going to this link. Yeah, yes, it is. So we could hyperlink. It opened it on this one, so we'll bring it over. So yeah, if you follow that hyperlink in the slides that were sent out, you can see in the tutorial section, there's installation. Of course, I know we introduced this. It's on PyPy now, so you can pip install it. But if you needed to install it from source, obviously we are an open source tool. So the source code is on GitHub, and you can build from source if you prefer. And then, like we said, each of these sections that we went through yesterday and this morning has its own whole tutorial section. So vector function arguments with some text to address it and some code examples, including then the standard math operators we went over and scalar operators. Then you get really useful tables like this of, all right, what are the functions that are exposed to a user for a vector function? What's it actually doing? Same thing for your vector norm operators, stacking, a summary of stacking and matrices, the discussion on conditionals, style and organization. So lots of extensive documentation, like we had said. Again, there's ODEs, so this walks through in the same order of how we walk through the tutorials of building up complexity. So you now have had tutorials for vector functions, but if you need to clarify, how do I define an ODE class in asset so that I can instantiate something that spawns off integrators and spawns off phases, there's something on that. I know integrators we went over yesterday and were able to get into some of the details, but you might have likely wondered about maybe some more details on event detection, derivatives and parallelization, more details if you're feeling stuck on the control laws that we went over. So yeah, the documentation is a great source to kind of look through. So we've now got, today we went over optimal control problems. So there's a whole page on that, on how do you initialize these optimal control problems. Again, discussion of your transcription methods, an overview of mathematically and syntactically what are the constraints or the phase region flags, with plenty of code examples and text to support those code examples. So hopefully between this training, the recordings, these slides and their examples, and the documentation, you don't feel like you're in the dark on how to use asset. There's a lot of resources now to show how do you formulate problems with it. So on top of that, we've got some other things that we didn't have time to get to, like a more in-depth scroll of SciOpt, the underlying optimizer, on what's going on under the hood, as well as what are some user settings that you can tweak. Remember we said an optimizer is instantiated as member variable. You can expose these different users and user change tolerances and constraints. So good extensive documentation on that, discussion on the convergence flags and multi-threading, and a discussion on what do each of the things in the terminal scroll of SciOpt actually mean, and what are they representing, other than just the very obvious color coding. Green is good. And JET is our native parallelization tool that you can parallelize and trade studies and run multiple OCPs at the same time. I know we discussed a little on adaptive mesh refinement, so we discussed the mathematical background, as well as what the search methods are for checking where mesh refinement needs to happen. And then there's a whole utility section talking on, I know yesterday we got a question about higher order interp tables, like second or third order interp tables. Okay, so I think we're ready to get back up and running with this final set of slides. I know we've only got one set of slides left. This is going to be a little bit longer because it's got more practice exercises where you guys as users can follow along and keep trying to implement these problems, leveraging the topic of this final presentation, which is the Astro library. So we're going to do this set of slides for a little bit longer, and then we'll take a break during these slides to go to lunch a little bit later on. And so then we'll pick back up after lunch to finish out the training on this. We also just wanted to send out a quick reminder that we didn't forget about those of you who asked about Mac support. We are looking into that on the back end to get that unofficial support, make the modifications we need for that unofficial support to be a little bit easier to use. We haven't forgotten about you.